In this chapter, we are going to be finishing up our discussion of thermodynamics, and in doing so, we want to look at the concept of equilibrium in greater depth and utilize this particular concept to further study what we refer to as chemical and phase equilibrium. In reacting systems that we just covered in chapter 13, what we saw was an equation that could be written that corresponded to the processes occurring as certain substances that we called fuels react with certain substances that we call oxidizers to form new substances that we call products. And in that particular analysis, we used conservation of atoms in order to make sure that we properly balance the number of atoms between the products and the reactants. And we also used the concepts of thermodynamics in order to determine the heat release associated with those types of reactions. And in chapter 13, we primarily dealt with an equilibrium system, as we have been throughout thermodynamics, dealing with single phases. Most of our substances were of the gaseous phase, even though we could possibly allow liquid phases to be associated with the products as well as the reactants. And so in this particular chapter, we want to look at what happens when we have multi-component, multi-phase, non-reacting systems as well as reacting systems. And we will be doing that with the introduction of what's referred to as the phase rule. So the first thing that we want to discuss is the equilibrium combustion. And so whenever we have a system that is in thermodynamic equilibrium, and typically that's how we have been discussing the various states that we go between in our discussion of thermodynamics, we say that a system is in equilibrium when it is isolated from its surroundings and that there are no macroscopic observable changes in that system itself. We typically make the assumption that the equilibrium system is at some uniform temperature, and upon reaching a uniform temperature, we imply that that particular state has a chemical equilibrium associated with it, and that the various molecules and atoms that exist are in certain amounts, and they aren't changing from one amount to another amount, even though the atom balance may allow such a change to occur. And so, as we then discuss this concept of equilibrium combustion or chemical equilibrium, we're going to look at a simple compressible system of a given fixed mass in which we assume that the temperature and the pressure are uniform with position throughout, so they're uniform throughout the system itself. And we could say, in the absence of overall system motion, as well as ignoring the influence of gravity or potential energy differences, we can write an energy balance in a differential form, as we saw back in chapter 2. And that first law of thermodynamics, as we called it, as we go from one particular state to another particular state can be written as the change, the change in the internal energy, the differential change in the internal energy, and how it's related to what we refer to as path-dependent changes in path-dependent effects due to heat transfer and work. And so this was the energy balance in differential form that we have been dealing with over the last 2 semesters of understanding thermodynamics, is that the differential change in the property of the system, the internal energy of the system, is directly related to the heat transfer and the work. And the amount of heat transfer and the amount of work that occurs are what we refer to as path-dependent functions that basically are not path independent, but rather path dependent. And so that was our energy balance in a differential form. And then if we make the assumption that volume change is the only work mode, okay, and that pressure is uniform with position throughout the system, we can then say that this path-dependent work term, this delta W, can be written by the equation P delta V. And so that was the form that we used when we had volume or boundary movement for a system that was at some pressure with a volume change. And so that pressure times a volume change corresponded to work, because work is just force through a distance. And so upon writing the differential form of the work in our first law, replacing it with this form here, we then can solve for delta Q over on the left-hand side, and that being then equal to the delta U plus the PV. So all we have done is substituted the PV term into the right-hand side with the negative sign and brought it back over. And so we have this particular form associated with our equilibrium system. The change in the heat transfer giving rise to a change in the internal energy plus a work-dependent term. Now we can also utilize our second law of thermodynamics, and our second law of thermodynamics related for us the concept of the property entropy, and how entropy was related to that differential change of heat transfer occurring through the boundary at some temperature T. And so we saw that when we had a uniform temperature system, that the heat transfer amount divided by the T, it was then related to the change in entropy with an additional term that corresponded to irreversibility. And we called that delta sigma, or the entropy generation term. So this was not a conservation of entropy, but rather our entropy equation that we introduced back in chapter 6. And so our entropy balance equation basically told that in the absence of any irreversibility, that the amount of energy of entropy change was directly related to the heat transfer divided by the temperature that the heat transfer is occurring at the boundary itself. And so, in order to account for any irreversibility in our balance, we'll keep this delta sigma term in. And now by taking this term and the previous term, we now can rewrite the previous term here. We can substitute the delta Q, and upon doing that, we then can show that this relationship holds between the last two equations. So in essence, that is the equation representing the first and the second law of the system by eliminating the delta Q. And so it's talking about what's happening to the change of entropy and the change of internal energy, as well as the pressure volume change, and how those three terms combine then represents the irreversibility associated with actual processes. And so what this basically tells us is that entropy is produced in all actual processes and is only conserved, if we want to think of it that way, if this right-hand side is equal to 0. So by saying it's only conserved in the absence of this term, it's basically saying that entropy change, or the production of entropy, is related to the effect of these two properties for the system as it undergoes change. And so what this tells us, 14.1, this tells us then that there is a direction that any process is going to occur. And since only processes are allowed to occur if they have a delta sigma that's greater than or equal to 0. What this is saying that at this right-hand side of 14.1 is either going to be 0 when we have no irreversibilities occurring, or it's going to be a positive when we do have irreversibilities occurring. And so this equal sign then can be replaced by a greater than or less than 0. And so this equation 14.2 then is telling us the direction for which entropy and internal energy and volume are going to change in a process as we allow the process to go forward. And so this particular equation then is, if we look at the left-hand side can be thought of as a function, plotting the function entropy as a function of the direction that the system is undergoing. And so what we have here, on the x-axis is the other components of the systems, the other properties of the system. And so what this tells us is that a system will basically always have an increase or 0 change in entropy. And so a process will go from state 1 to state 2 only such that there will be an increase in entropy or no increase in entropy for a constant internal energy, constant volume process. And so if we say delta U is equal to 0 and delta V is equal to 0, that would be a fixed mass system with a certain amount of energy associated with it. And what this tells us that entropy and temperature will then either the combination will be equal to 0 or will be greater than 0. And so the system, if it starts over here, will end up at the top of this hump, or if the system starts over here, it will then go to the top of the hump. And so we will, a system will go to a state of maximum entropy. And that would correspond to the system going to an equilibrium condition. So what does this mean with respect to what we have just covered? What this means is that at this particular time we said, let's assume we have fuel and we have oxidizer coming together, and we balance the equation, and we say that what comes out of that reaction are certain products at a certain temperature and a certain pressure. And so then we ask ourselves, is that mixture of the products going to stay in a certain combination associated with the balanced reaction. And what this will tell us is that the various components of the reactants, or excuse me, the various components of the products are going to shift in order for a state of maximum entropy to occur. Okay, and again, that's a statement associated with the first and the second law of thermodynamics, that the equilibrium condition that will come about will be such that it will try to shift the system to a state of maximum entropy. Now, up to this point in chapter 13, we typically would solve the first law, and the first law told us that the amount or the temperature associated with the products based on its volume and the various components would be a given. And we never said much about entropy in chapter 13, except for determining how much entropy changed. Now in chapter 14, we now have another statement in that not only will the temperature and the pressure take on certain amounts associated with the combustion process, but now we say that the actual final mixture is going to drive itself toward a state of maximum entropy. And in just a few slides here, we'll then see what we mean by that. Now, when we introduced in chapter 10 the different differential forms of properties, we introduced some other properties other than entropy and enthalpy and internal energy. We introduced another property called Gibbs function, and we said that the Gibbs function was just this capital G, which was H minus Ts, just associated with other thermodynamic properties. And we can do with this G function obtained, we can then look at the differential form of that particular property and utilize the various differential relationships that we've seen before, and we can then rearrange some terms, and that's all that's being done here. When we take the differential of H, we know that H is a function. H is equal to U minus PV, or U plus PV, and so when we take the differential, we get a delta U here, but then when we take the differential of PV, we have a PDV plus we have a VDP, and then we have the minus TDS. When we take the differential of that, we have a TDS minus an SDT. So when we take the total derivative of G, we get all of these terms. And then again, we can rearrange these terms, and then upon rearranging the terms, we can get it into a form similar to what we saw before with equation 14.2. And upon doing the similar relationship that we had with 14.2, we then can show that this dg minus this term and plus this term is now going to be minus or less than or equal to 0. Again, because of the second law introducing the entropy generation term. And so the difference between 14.4 and 14.2 is that in 14.2, the left-hand side is greater than or equal to 0, and in 14.4, the left-hand side is either less than or equal to 0. And so what this tells us now, if instead of looking at the concept of entropy for a constant internal energy and volume, we looked at this Gibbs function at a constant temperature and pressure condition, we see that the Gibbs function will be driven to a minimum as we go to equilibrium. So once again, we have an equilibrium state that is defined by the Gibbs function. And then as we have the tendency of going from one grouping of molecules in that particular mixture to other groupings of molecules in that mixture, what we find is at a constant temperature and pressure for the overall mixture that the final condition will occur when the Gibbs function is minimized. And so the equilibrium condition then would correspond to where that term is a minimum. And so what we have now done is we've looked at the equilibrium condition as either being the point where we have maximum entropy or the point where we have minimum Gibbs function. And they correspond to two different kinds of condition. One condition is when we have a fixed energy, fixed volume. And so one would think of that as a container that consists of a certain mass of material confined within a certain volume. And then the second one would be where we have maybe like a flowing system, where we have a mixture of material flowing through the system, wherein there is a temperature and a pressure associated with the flowing system. And so this lends itself to a control volume type of combustion system, whereas this lends itself to a control mass combustion type of system. In chapter 10, we broke down this Gibbs function in terms of the individual components making up the mixture. We introduced that the change of this mixture Gibbs function as a function of individual amounts of moles of each of the mixtures, holding the temperature and pressure and all the other mole fractions constant. We called that the chemical potential for each individual component. And that previous equation representing equilibrium then is no more than just a summation of the chemical potential weighted by the differential change of each of the individual components and setting that equal to 0. So that is our equilibrium criteria for a mixture as it switches equilibrium compositions in order to find the one that is the equilibrium condition. When we have just a single phase ideal gas mixture, the equation that this represents can be simplified as just a summation of the Gibbs function for each of the components multiplied by its corresponding number of moles. And we can then relate that to the mole fractions can be related to the partial pressures associated with the individual components making up the mixture itself. And so we'll see this in a later calculations. Again, it's all looking for what is the final equilibrium composition associated with a mixture that has just single phases associated with it, in this case the ideal gas phase. And so next time what we're going to do is we're going to look at how this affects what we say is at the in the products of a combustion reaction, and we'll look at some examples. And so we'll pick up here next time then.